So, prolonging our discussion about the conservation of mechanical energy, wherein we did the case of constant gravitational force, which we established that it is a kind of a central force, wherein the conditions of the central forces, conservative forces, was true. Today we'll build up on that concept and discuss the conservation of mechanical energy in the context of a spring with a mass attached to it. We'll talk about the potential energy of the spring, which got to be taken as massless, etc., etc. It during its extension and contraction, the spring does not lose any kind of an energy by means of heat, etc. Okay, so here we have the force of a spring which is proportional to x, and the restoring force is equal to minus kx. The two are in opposite direction. This is what is proposed by Hooke's law of elasticity, okay, wherein we get a relation of this kind. Fs, the force of the spring, is proportional to x, and therefore the restoring force Fs, the force of the string, is equal to minus kx, where k is the spring constant, which is expressed in Newton per meter. And just to tell you that the spring is said to be stiff if the value of k is large, in which case the extension for a given force will be small. Okay, that is why we call the spring stiff in normal terms. And if for the same force the extension x is large, then k will be small, because there is a relation between k and x, that the product of this depends upon the applied force. So the applied force or the restoring force which exists, I can give the example here, that this is our spring, which is massless, which is attached to a rigid wall. A rigid wall whose very massy and cannot be disturbed under the described motion. So here in the first case, the mass is attached, mass m is attached to it, the spring, and this is the condition of equilibrium. That is, the force acting on the spring is equal to 0. I told you that there has to be an environment of tension while the position of the mass is disturbed. So here I take this position of the mass as x is equal to 0, and at that time the force which is acting on it is also equal to 0. Later on, what we do is we pull this mass to our right to provide an extension, and that extension is, say, x meters. So in that case, there is a force which is acting on it. This is pulling force. Of course, there will be, at that time, there will be a restoring force in the opposite direction, provided by the kind of tension, and this actually will reflect a force actually over here, okay, which will be equal and opposite to this force which is pulling it in this direction. Later on, if we compress it to a length x, then what we get is that if some condition of compression, I am just writing xc for that, we will be using the term x in our calculations, then we find that in that condition, so what happens is, if I pull it on this side to a maximum extension plus xm and release the system, this surface, these surfaces that I have shown over here, they are frictionless. So there is no loss of energy due to friction. So what happens is that when this is released, then right now, just like that, I am saying that in the maximum condition, the potential energy associated with the system will be maximum, its velocity minimum, and therefore the total energy of the system will be the potential energy at this displacement xm, which has been shown over here. Okay, the relation between the force in newtons and x in meters is shown by this line which comes over here, and this is actually F is equal to minus kx. And we find that because force into displacement is the work done, so I am just showing as to what is the amount of the work done in the displacement that takes place from this position to this position, or from this position to this position, which has been shown over here in the form of the area. And because x is negative when the force is positive, and because x is positive when the force is negative, okay, this is what has been shown over here in this graph, and this turns out to be equal to the area, which gives us an idea to calculate the work done on the system is minus half kxm squared, which I can show with the help of this relation. If it is disturbed from position x is equal to 0 to x is equal to xm, then fs dx turns out to be equal to, because fs is equal to minus kx, so I take this under the integral sign 0 to xm kx dx, or this is half kx squared between the limits 0 to xm, and when I substitute the limits, I obtain the relation minus kxm squared here. But this is the work done by the internal force of the system. The work done by the external pulling force will, however, be plus half k xm squared, and this actually, the external pulling force is the force which overcomes the spring force which is given by Fs is equal to minus kx. Okay, so whatever we discussed about this condition, when it is pulled and there is an extension in the spring system, the same is true for the compression also, which is the third case which has been taken over here. When it is compressed, and I show that the compression is minus x, which for the sake of clarity I'll write it xc. X in this case is negative, but Fs is positive. Okay, and xc is less than 0. So this describes the system, and if I calculate the work done by the spring, I find it that this work done by the spring turns out to be equal to half kxc squared. At the same time, like before, I will say that the work done by the external force is equal to plus half xc square. Okay, so I can therefore write that my kx dx, yani f as a function of x into dx, from an initial position xi to a final position xf, if I calculate the work done by the spring, it turns out to be equal to, and as I told you that k will be out, this is x square by 2, and the limits are applied xi or xf, then I obtain this as half kxi square, the initial position is square, and the final position is square, which shows. Now, what we find that the work done is, it depends upon, k is a constant for the system. So it depends upon xi and it depends upon xf, these two positions. And these are the end points of the system of disturbance that we have created over here. And this is one of the conditions, of course, for central forces, which depend upon the end points only and not on the path. I may add, for the benefit of those students who have learned something about the electrical phenomena, electric fields, electric forces, electrostatic forces, etc., which are said to be central forces, because the E dot dr is path independent. Integral E dot dr. And here E is not a force, E dot dr. So if it is in the direction x, it will be E dot dx, E dot dy in direction y, E dot d in direction z, and in any arbitrary direction from one point to another point, if we move on any path and integrate this, then it is said that it is path independent. Okay. Allow me to add that if we calculate this E dot dr over a closed loop, maybe the path is like this, then of course the total value of integral E dot dr turns out to be equal to 0. So this is one of the forms of a certain relation that we discuss in the electrical system. Same is true for the mechanical systems also. Okay, and that is why we'll show that in the case of the compression and extension of a spring, for the various conditions that we have taken, in the wall is rigid and the surface on which the mass is made to disturb this position, they are all under certain conditions, massless, frictionless, this, that, this, so many conditions and constraints that we take. Okay, so this is one of the conditions. And if I'm allowed, so only the end points. So if it is only the end points that we are talking about, then what we can write is that if we take the block to a certain x and then bring it back under the same conditions to the same xi, then what we can write is that my Ws, the work done by the spring, will be equal to minus times integral kx dx, this is by definition. And now if I take the limits xi back to xi, okay, the initial and the final positions, they overlap each other, then I will write this as k half k from that relation xi square minus half k xi square, and the same thing subtracted from the same thing. This will, even a child will tell you that this is will be, what is the beautiful 0. Okay, so the work done by the spring in a cyclic process. So work done in a cyclic process, work done in cyclic process, cyclic, I write like this, process that occurs in the system, this is equal to 0, as was found also in the other case, in the case of gravity. And so what are the things? There are three things which we have arrived at. There are three things which we have arrived at, and these indicate that this force is a central force. Number one, spring force is position dependent. Spring force is position or configuration, is position dependent, good, dependent, Number two, that the work done depends only on initial and final positions. Work done, I can write in short, this English is a function of the initial position xi and the final position of disturbance xf, which could also be equal to the initial position xi, in this case of the cyclic thing. So we can say in the cyclic case, which I have just shown here, cyclic case, the work done is equal to 0. So these are the three important features which are in consonance with the requirements of a conservative force. So this all indicates that our force is a conservative force. Like in the last case, here also. So the conservative force, then conservation of energy holds. Okay? So now we have established that the force under consideration in this simple problem is a conservative force, which we see that at x is equal to 0, the equilibrium position, the equilibrium condition, the potential energy function Vx can be written as kx square by 2, which is of course a scalar that from where we will obtain the vector, the force. So if I multiply by -1 and do the exercise of dv dx, it will turn out to be equal to minus k into 2x upon 2, which turns out to be equal to minus kx, and which is the spring force. So we can see that the condition of the spring force minus kx, f is equal to minus kx, is obtained from the potential energy function, which is definitely a scalar. Now, if we extend the mass m to a limit xm and then released from the condition of rest, when the initial kinetic energy is equal to 0, then we can write for any arbitrarily chosen point x between minus xm and plus xm, the condition on this side, maximum on this side minus xm to plus xm, and then write the principle of conservation of mechanical energy. So at that position, because the velocity is equal to 0, so the kinetic energy is equal to 0, half kx square xm square is equal to half kx square, which is the potential energy at that instant, general point x under consideration, plus if the velocity achieved has been v, then half mv square is kinetic energy, and therefore this is the conservation principle which has been applied to this situation. Okay, so what we see is that the potential energy of the system from one position to another position, it varies, as also we'll see that the kinetic energy is varied. So for the conservation of energy, let us take a special point, and that's the equilibrium point, x is equal to 0, and there we find that if we compare the things, half mvm square is equal to half k xm square. So one of them is the maximum kinetic energy and the other is the maximum potential energy associated with the system. The maximum kinetic energy is equal to the maximum potential energy because here the potential energy is equal to 0 and here the kinetic energy is 0. So if we work on that, then half cancels with half, and Vm square will get as k upon m xm square. Okay, so I can write Vm as equal to plus minus of under root k upon m into xm. Now k, the spring constant, is because the force is equal to kx. Okay, the value of the force, the magnitude is equal to this. Okay, so from that we find that the k, the spring constant, is in newtons per meter. And if we do the dimensional analysis, then newtons is mLT minus 2, meters is L, so L and L cancel and we get m upon t square, or mt to the power of minus 2. If I divide this k by m, then mass and mass cancel, and what is left for us is t to the power of minus 2 per second square. And when I take the root over of k over m, this is an important aspect, it turns out to be equal to t to the power of minus 1, which is per second. Okay, now I would just like to tell you that this f can be written as m d2x upon dt2 from Newton's second law. And when I equate it to this, then m comes over here and we get d2x upon dt2, which is the acceleration associated with the particle, is equal to minus k upon m into x, which I can write, we will write, I will write as minus omega square x. Why? Because k is positive and m is also positive. So we are taking it, a positive divided by a positive must be equal to a positive, which is taken as omega square, and you know that this is the angular velocity given by 2 pi over capital T, and 1 upon capital T is equal to nu, so this is per second. Now here is the plot of energy versus x. Okay, and if I plot from the position of minus xm when the potential energy is maximum down to this and again like this, so this graph shows, and this graph, the nature appears to be that of a parabola. This one also appears to be that of a parabola. At all instants of time, when this is 0, then this is maximum. And any instant of time, if we sum the potential and the kinetic energy plus the potential energy, we get a constant value which is shown by this line, and of course the V is shown by this and K is shown by this. So this is what is exactly in this particular case. So I have established in the due course of time that the law of conservation of mechanical energy is applicable to systems which subscribe to what? Which subscribe to the condition of central forces, conservative forces, and conservative forces we have over here in this condition, as well as we had in the condition of a falling freely under gravity, ball or body or anything. There also the force was taken as conservative, and the law of conservation of mechanical energy, which is the sum total of the potential energy and the kinetic energy at any instant of time in the motion of the body, is equal to, is invariant, doesn't change. Okay, so this is what we have established. Next, we will discuss very briefly that this energy, I said it is it is the very concept which has been described earlier as a romantic concept. In romance, things move from one format to another format. So the energy also has many formats, many forms of energy, okay, and the conservative laws do hold. One of the forms of energy is the obvious heat energy, where we use the unit of calories. Chemical energy, where endothermic and exothermic reactions take place. The sum total of the energy of the reactants, which we get on this side, the other side of the equation, and is more than the sum total of the energy on this side, and then endothermic, exothermic, and this is the very beautiful concept. The chemical energy, then we have electrical energy, half mv square, I square upon r, etc., etc. And then we have the famous relation from the special theory of relativity, that one of the forms of energy is mass, or one of the forms of mass is energy. It's called the mass energy equivalence, and the beautiful relation which Einstein gave, for which he didn't get the Nobel Prize, okay, E is equal to mc square, the most famous equation of Einstein. In fact, Einstein got the Nobel Prize after many years, after many times he was declared a candidate, and finally it was given for the photoelectric effect, which was a beautiful concept that you cannot subtract 5 out of 3, but 3 can be subtracted from 5. This was the h nu minus h nu naught is equal to. So this was a beautiful concept. I told you that in physics, what is simple is the most beautiful. And so he got it. In fact, in 1905, Einstein wrote 3 papers, landmark papers. One was the special theory of relativity, and the other was this photoelectric effect, and third was the explanation of Brownian motion, but he got it for that. Then you have the nuclear energy, where fission and fusion, etc., etc. I'll briefly tell you about that, and then I will come to power, okay, power consideration in the next lecture. So long, see you, hope you enjoy.